All right, this is our theory of elasticity problem 4-7.1, and I want to work this as an example. It gets a little involved with the algebra, but we'll see how this works out here. And it'll give us some practice not only with the algebra, with some of our concepts of elasticity. So it says, let an isotropic elastic material in the xy plane be subjected to stress components. Sigma 1,1 is equal to 0, sigma 2,2 is equal to sigma 1,2 is equal to tau. U1, U2, and omega is equal to 0 for x1 and x2 equal to 0. And U1 and U2 denote the x1 and x2 displacement components, and omega denotes the volumetric rotation. Show that the circle x1 squared plus x2 squared is equal to a squared is deformed into an ellipse. And for the case of tau is equal to 0, show that the major and minor axes of the ellipse coincide with the x1 and x2 axes and express their lengths in terms of A in the elastic properties of the material. All right, so let's kind of start here talking about what we have. So we have a stress tensor that looks like this. And in the plane, they're talking about the x1 and x2 directions. I'm probably going to switch this over to the x and the y directions. Right? And we have a circle. It doesn't have to be a circular object. It doesn't have to be a bar, but it could be a plate, and we have a circle drawn on the plate. That's probably a safer way to think of this. So we have a circle that's drawn on this plate that's subjected to tension and torsion, and we want to show that when we have our deformations, it turns into an elliptical shape. We're going to do this through the use of our strain displacement equations. Now, if you remember, we are in the section where we are looking at small deformations. And there's different ways to write this Hooke's law that we're going to use. We're in an isotropic material. So we're going to use the we're going to use the relations here that epsilon x is equal to sigma x over E minus nu sigma y over E. Sigma z is equal to 0, so I'm not going to write it down. Epsilon y is going to be equal to sigma y over E minus nu sigma x over E. Sigma z is equal to 0. Now, since sigma x is also equal to 0, this turns down to minus nu sigma over E and sigma over E. We also have some shearing strain, and I'm going to use the engineering shearing strain, gamma xy. Gamma xy is equal to tau divided by g. If we want to, we can note that our shear modulus g for an isotropic material is equal to E over 2 divided by 1 plus nu. For this, I think it's going to be simpler to just leave it as g, and if we need it later on, we can make that substitution. Now we need to look at strain displacement. In general, for small deformations, epsilon ij is equal to 1/2 partial of ui with respect to xj plus the partial of uj with respect to xi. This problem also mentions rotations, and rotation is the anti-symmetric part of the gradient tensor. So that would be 1/2 partial of ui with respect to xj minus the partial of uj with respect to xi. So we'll have that handy as well. Well, if we put in epsilon 1,1 and we take into account the half, epsilon x will be equal to the partial of u with respect to x. Here we have the u displacement in this direction, we have the v displacement in that direction. And if we look at epsilon 2, and we go through the information here, this will work out to be the partial of v with respect to y. And given that this is an engineering shearing strain and these are tensor shearing strains, if we double the tensor shearing strain for 1 and 2, we will end up with the partial derivative of u with respect to y plus the partial derivative of v with respect to x is equal to gamma xy. And just to have it so we have it handy, omega 1, 2 is something that we need. I think what they're wanting is omega 1, 2 right here. It would be 1/2 the partial derivative of u with respect to y minus the partial derivative of v with respect to x. All right, so we have all of our equations here in handy. Let me save this before we get too far. All right, so we've discussed this approach a couple times for some different examples. What we're going to do to start off with is we're going to take and we're going to integrate this equation for u, we're going to integrate this one for v, we're going to get some information, and then we're going to pull some additional information by looking at this equation for gamma xy. All right, so let's do this first one. Let's write it over here. Partial of u with respect to x is going to be equal to minus nu sigma over e. So this is a partial differential equation, so if we integrate both sides with respect to x, we're going to have u is equal to minus nu sigma over e times x, plus we could have a function of y, and inside that function of y could be a constant. We're going to leave it just like this for now. All right, now we're going to take a look at the partial of v with respect to y, and that's equal to sigma over e, in which case we'll do the same thing, and we'll get v is equal to sigma over e times y and a second function of x. Now, since we're in a plane and our problem specifically stated we're looking at functions of x and y, we have not explicitly accounted for any z dimension in this arbitrary function. All right, let's take our partial derivatives so that we can put them into our shearing strain equation. The partial derivative of u with respect to y is going to be equal to df1 dy. Partial derivative of v with respect to x is going to be equal to df2 by dx. All right, let's put those into this equation for gamma xy. So we have df1 dy plus df2 by dx is equal to tau over g. So if I want, I can solve this for the first function. Like so. All right, let me make a little bit of room here. All right, so when we look at this equation, we have a derivative of function f1 with respect to y is equal to something minus a derivative of another function with respect to x. Well, there can't be any x's and y's left in either the left side or the right side. So this entire thing is going to have to be a constant, and I'll call that constant c. Well, that allows me to work with this a little more easily, so I have two equations now. I can find then that f1 is equal to c times y plus another constant of integration, call that a, and then if I pull this to the other side, I can have df2 by dx is equal to tau over g minus c, in which case f2 then will be equal to tau over g times x minus c times x plus another constant of integration. So now I have a form of the equations for f1 and f2. So instead of having it written like this, we can just write, I'll put it down here, u is equal to minus nu sigma over e times x plus f1 and v is equal to sigma over e times y plus f2. All right, now we need to work a little bit more, given the information that we have. We need to see if we can figure out A, B, and C. Let me save this again. All right, the first clue that we have is in here when x1 and x2 are 0, then u and v are 0. Okay, so when x and y are 0, u is equal to 0. So that means A is equal to 0. V is equal to 0 and x and y are 0. So, okay, we have B is equal to 0. Now the last bit comes from our rotation equation here, and this W12 is going to be equal to 0. Now the half can go away, no problem. So effectively we have partial of u with respect to y is equal to the partial of v with respect to x. Using this equation here, the partial of u with respect to y is going to be equal to c. The partial of v with respect to x is going to be equal to tau over g minus c. So in this case, 2c is equal to tau over g. So c is going to be equal to tau over 2g. So we have found that particular constant of integration. All right, now with that, let's rewrite our displacement equations, knowing what we know now, and then we'll get a new page. Let's see, here we have tau over g minus a half tau over g. That's going to give us a half tau over g times x. All right, let's take those equations and we'll start with that to see if our circle turns into an ellipse. All right, when we have displacements, the new position may be the new position of a point x star. So maybe we were here at a point x, y, and now it's over here somewhere at a point x star and y star. Maybe it's further to the right and further up. I don't want to make this too confusing. But x star would be equal to the original position plus the u displacement, and y star would be equal to the original position plus the v displacement. Let's write it here. So I'll have 1 minus nu sigma over E times the quantity x plus tau over 2g times y. And my y star would be equal to, I want to write the x term first for a reason, tau over 2g times x. I'll have a plus 1 plus sigma over E times that quantity times y. All right, so I'm going to solve for x and y in terms of x star and y star. And I want to eliminate one of my variables. All right, so what I'm going to do, say I want to eliminate the y. Then I'm going to take and I'm going to multiply this entire equation by 1 plus sigma over E. And then I'm going to take and I'm going to multiply the bottom equation by minus tau over 2g. And then I'm going to add these two together. All right, keep an eye on my algebra here. I'm going to have a 1 plus sigma over E x star, and I'm going to have a minus tau over 2g times y star. That's going to be equal to 1 minus nu sigma over E, 1 plus sigma over E times x plus tau over 2g times 1 plus sigma over E. It's going to cancel out with minus tau over 2g times 1 plus sigma over E. All right, so I'll go to this term here. Be a minus tau squared over 4g squared times x. So if I solve for x is going to be equal to 1 plus sigma over E x star minus tau over 2g y star divided by 1 minus nu sigma over E times 1 plus sigma over E minus tau squared over 4g squared. All right. Let's save that page. I'm going to keep this on here, and then we're going to do something similar, and we'll solve for y. All right, so I have my starting equations again. Now I want to eliminate the x term. So I'm going to take and I'm going to multiply the top equation by tau minus tau over 2g. And I'm going to multiply the bottom equation by 1 minus nu sigma over E. I'm going to add them together. And keep a close eye on my algebra. Over on the left-hand side, I'm going to have minus tau over 2g x star and 1 minus nu sigma over E times y star. And that's going to be equal to this term times this term and this term times that same term. So this x term will annihilate each other. I'll have a minus tau squared over 4g squared y, and I'll have a 1 plus sigma over E times 1 minus nu sigma over E on the bottom, well, not on the bottom, times y. Now I'm going to take that and I'm going to solve for y, the new component. So I'm going to have minus tau over 2g times x star plus 1 minus nu sigma over E times y star, all divided by, I'm going to write it this way, 1 plus sigma over E times 1 minus nu sigma over E. It's the same term right here. Then a minus tau squared over 4g squared. Okay, so those two terms have identical denominators. All right. Now, we started with a circle. Whatever you want to put here, a squared. That's what it started with. We had a line, a surface, curve. It was a circle originally before the deformations were applied to it. Now we want to see if this thing turns into an ellipse. We're going to take these and put them into here. Time for a new page. So we have x squared. I'm going to worry about the denominator later. Let's just take a look at the top. It's going to look something like 1 plus sigma over E squared x star squared. We're going to have a mixed term. It's going to look like minus 2, 1 plus sigma over E tau over 2g x star y star. And then we're going to have another term that looks like tau squared over 4g squared y squared. Okay, so that's all comes from this. Then we're going to have this squared, which is going to look like a tau squared over 4g squared x star squared. Need a squared right here. I'm going to have a mixed term that's going to look like a minus 2, 1 minus nu E sigma over E tau over 2g x star y star. And then I'm going to have a term that looks like a plus 1 minus nu sigma over E squared y star squared. of that is going to be over one plus sigma over E times 1 minus nu sigma over E minus tau squared over 4g squared, quantity squared, and then that stuff is going to be equal to my A squared. All right. If we group terms, maybe we can do a lot more algebra to make this look prettier. But if we group terms, what we're going to see is that we have some kind of term times an A times an x star squared. We're going to have another term that looks like x star y star. And we're going to have another term that looks like something times y star squared. And then, it's going to have something like another thing squared over here when I multiply this over and all that. Okay, so this is an ellipse. It'll have a certain angle of rotation, depends on the ratio of the tension and torsion. All right, now the second part was for the case tau is equal to 0, show that the major and minor axes of the ellipse coincide with the x1 and x2 axes. Then it says express their lengths in terms of A and the elastic properties of the material. Well, if tau goes to 0, then this coupling term goes to 0. All right, we're going to be left with something that looks like 1 plus sigma over E squared x star squared. And then, let's see, this term goes away. It's got tau in it. This term goes away. This term goes away. That term goes away. And then we're going to have a term that looks like plus 1 minus nu sigma over E, that squared, y star squared, is equal to my A squared times 1 plus sigma over E 1 times 1 minus nu sigma over E squared. All right, so based on that, I will let you figure out what the major and minor axes lengths are in terms of the elastic properties. Some of these can be a lot of algebra, and I want to say I really don't want the algebra to detract from understanding the basic concepts. So let's review the basic concepts. We started off with our stress tensor. We used strain displacement and Hooke's law. First, Hooke's law to find our strains, strain displacement to find our displacements. We had to integrate a set of partial differential equations, find our constants of integration through the boundary conditions that they gave us. Once we found our displacements, then we can find the final positions, because the final position is the initial position plus the displacement. All the rest is just kind of window dressing on this problem. So that's it for problem 4-7.1.